Hello everyone. Today I'm going to co-present with Remy Durafor, who is technical lead for the Lava team. And I'm Loic Poulain, part of the support and solution team in Linaro. So we are going to present you automated testing of Bootloader in Lava. Yeah, that's right. So, why testing Bootloader? Simply because any other piece of software, Bootloader is subject to bugs and regression during development. The Bootloader is also a critical part of the system. If it fails or have some issues, it can prevent part of the system or the whole system to accomplish its primary function. Nowadays, this is also a critical part in terms of security because it's often a chain of trust element which need to, for example, check the kernel, the signature of the kernel, of the rootfs, and so on. And depending the execution level, also it has much or less access to the hardware. Also, we are today focused on second and third stage bootloader like LK, little kernel, or also U-boot. And this kind of bootloader is quite a small OS now. It implements some advanced feature, have a lot of driver, implements stack, network stack, fast boot protocol, TCP/IP, TFTP, and new standardized interface like eBBR. And all of these need to be tested as well and validated. But bootloaders are much less tested than standard OS like the kernel or user space, simply because we suppose that if the bootloader runs and launch the primary system, that's okay. We don't need to touch it, and we can live with it. I'm sure the audience is already aware about what is Lava, but just as a reminder, Lava is for Linaro automated validation architecture. This is a system that simply allows to test in an automated way your software to real hardware. For example, a basic use case is I develop on a kernel, I push a patch, I commit a change, and I want to make sure that the software I change does not have regression on real hardware, and I can still boot on, for example, a Dragon board, a Raspberry Pi. So I can use Lava for this automated testing. But this is not limited to boot testing. You can also test feature, system, power consumption of your device with a new software. Lava is organized in a server dispatcher model. So the server is the primary UI interface, but it also stores the test result and schedules the different test jobs. The dispatcher is here to run the job itself and boot the device under test, deploy the image that we need to test, and launch the test. Lava is scalable and distributed. You can have a simple lab with only one device, but you can also grow your labs and add dispatcher, device, and all of this can be remotely around the world.
So in this example, just to show you a bit more what Lava is doing, so we do have a Raspberry Pi or any board, doesn't really matter. So you need a way to control the power, so power controller. A way to access the serial, and then you need also some external services like TFTP server and FS server, depends on the hardware you want to access. So the dispatcher, as Loic said, which is part of Lava which is responsible for talking to the board directly. That's the only part that talks to the board. So the dispatcher needs to have access to all these elements. And if you want to test a board, you will provide to the dispatcher a job configuration, which is a description of the resources you want to test on your board. So DTB, kernel, rootfs. And you will also specify the method to use for deploying and booting and testing. All of these go into the job definition. I will show one a bit later on. Obviously, you can have many boards on the same dispatchers, and you can have many dispatchers connecting to the same server. This will form a Lava lab. As Loic said, the server is responsible for all the web UI, storing the results, etc. So users are interacting only with the server, and the board are only attached to a dispatcher. That's why it can be remote if needed. So just to be on the same, to have the same vocabulary. So deploy, when we speak about deploy boot tests, deploy means providing, grabbing the software you want to have, so kernel, DTB, rootfs, all the test case, test definitions, script you want to have on the board. This will be what we call the overlay. So all the tests that you want to have on the board, it's called the overlay plus some helpers. And it also means setting up TFTP, NFS, etc., and putting all the right images. Booting means connecting to the serial, powering on the board, using the right tool for sending the binaries, and booting the board, obviously. And testing means running a script on the board itself, collecting the results, and sending back to the server.
Yeah, so here is a simple example of a Lava job on a Raspberry Pi. So this is in YAML format. We have first here on top, we have some metadata and data. We have the device type on which we want to run the test job. So here we want to run it on a Raspberry Pi 3. We have some other information like the timeout, the priority of the job, and the visibility on the UI interface. Then comes the actions. So we already speak about the action. Here is an example. For the deploy part, we select all the chunk we need. So we need a kernel, the module associated with the kernel, the rootfs, and the device tree blob. Here we can see that we retrieve all of these from the network. Then comes the boot actions. Here we select an NFS boot action. That means that Lava will automatically configure, interrupt the bootloader in order to run the kernel with the right NFS parameter in order to boot and mount the rootfs over the network. We have also some other interesting chunk. We have the auto-logging argument, which allow you to specify on which prompt you need to enter your logging in order to log on the system, and then which prompt you expect in order to launch the test. And last but not least, for sure, the test action itself. Here we select several test definitions from some Git repository. So we have some smoke test here. So now, when we usually test OS, we have some assumption and condition for this. We need a known file system because Lava will generate the test script, and before sending the image on the device to test, for example, the kernel and rootfs, Lava needs to inject this test in a file system. So Lava needs to have a known file system in which to inject the test script. We need also a way to provision the device. So this can be fastboot for Android device, for example. For the network booting, this can be TFTP and NFS. And for each device, we need a stable and unique identifier, because when you have a lab with several devices, you need to know how to communicate with these specific devices, and so have a unique ID. And you don't want to interfere with the other device when you test one. For booting the device, you need a UART console debug, because you need to check on the output of the console when the device has correctly booted or not. And you want to use this console as well for log to the device and to run the test, and also to pass the test results. You need a recovery method in order to recover the device if your software fails and you want to recover the device in an automated way. So you don't want to have to manually put the device off the lab and reflash the SD card, so on. So you want to have a recovery method. And for the test itself, we expect, we generate test scripts, so we expect a POSIX OS and shell. So that was, these conditions are usually filled, and we can easily test OS now. But testing bootloader is where the problems come, because on bootloader, even if you have some of them that implement shell, you don't have POSIX shell and POSIX system. So you cannot run the usual Lava test script. Anyway, there is usually no file system for a bootloader. This is usually a binary blob that is just executed, so you cannot inject any test on the bootloader. And maybe the more important point here is for deploying the image and the recovery, because the deploying method is usually implemented by the bootloader itself. For example, fastboot, TFTP. So if you deploy a bootloader to test which is buggy, which crash, which has several issues, maybe this bootloader will be unable to implement this deploy method. That means that you flash a bad bootloader and that's it. You cannot recover your board and you cannot flash any other bootloader. And some of the hardware and board implement low-level bootloader, primary bootloader, which support some deploy method like DFU and so on. But from experience, we see that many of the boards that implement DFU, for example, don't have any unique identifier. So this makes it hard to automate in a lab.
So now that you know that it's just not possible to test bootloader in Lava, let's look at how it might be possible. Let's say we want to try to test U-boot on a Raspberry Pi, but just an example, because everyone knows Raspberry Pis. So like a lot of other boards, you can boot from SD card, so Raspberry Pi, you can boot it. Usually you just put U-boot on the Raspberry Pi, and then you TFTP boot from the SD card. So we need a way to provision and to write on the SD card remotely. This kind of device does exist now. I will just present it in the next slide. So this is kind of solved now problem. The second one is to be able to have non-POSIX testing in Lava. So since the last release 1903, this had been implemented. So you just need to have UART access, and you can just test remotely a board. So the first thing, provisioning using an SD card. So you want to be able automatically to flash the SD card without having to unplug it, plug it somewhere else, write, and then replug it into the board. Obviously, because you want to do that so many times per day, just not possible. So you need a way to multiplex the access. Either the card is visible from the DUT, device under test, so the board, or ever is visible from the dispatcher, so you can flash. This is the kind of things you want, which is called SD wire. It's made by some Tizen people, technically Tizen contractors. So it's just a simple muxing. So you plug it, you put an SD card inside it. So ever the SD card is visible from the DUT, ever is visible from the dispatcher, and you can control that by software. And it works for most devices, not all of them. And it just solves the first problem, almost solve it. Not for all the board, but it's quite working. It's better than before, at least. The second thing is we won't have a POSIX shell anyway on the bootloader. So how does Lava interact with the board for testing? So we implemented a new feature called interactive testing. So all this code goes into the job definition in the test block. So instead of giving a Git repository with the test inside it, you will provide a list of commands that you want to run on the board. So for example, on this one, you will see commands. So I want to type DHCP. So Lava will just send DHCP enter, and he will have a list of messages to expect. If it's matching client bound to address, it's a success. If it's matching timeouts, it's a DHCP failure. And it's, I think, an infrastructure error. So it's matched as an infrastructure error, not a test error. So with this list of commands and list of messages, which is a bit long and painful to do, but you do it once, you can have all the things that you are expecting to see in your console. And Lava will do the matching for you. You don't have to do it manually and test everything. So for example, you can do some memory writes, memory reads, and see that I'm writing something in the memory and reading it just afterward. Is it working? You can have quite easy answers and quite interesting answers with that. So let's try to crash everything now. I think I have to do that. So I do have a board which is in staging. We did that with Mario just before, and Miloš too, just before with the Connect, so we try to do that. The action type, the deploy stage in this case is a bit specific. It's called flasher method. It's, I can try to make bigger. Can't make it bigger, sorry. That will be the maximum. Is it okay? Okay. That will be enough anyway. So the deploy method, you need a method called flasher. So it's a method that you can use for using the SD wire. So it's a specific method in which you put the commands to flash the board. So you will have to put the SD wire in to set the SD wire so that the SD card is visible to the dispatcher. Flash image, so just a DD on the right /dev by ID something, and then do the reverse for the SD wire, so make the SD card visible to the DUT. And then you just boot the board. We have a method to boot the board just to the bootloader, which is expected to be U-boot. So technically we just boot the board and wait for the bootloader prompt, interrupt it, and that's all. We don't do anything more, anything else. And then we will run some commands. So it will take some time to download the image because it's huge. So let's look at the previous one. So you will see, and I will see if it's working afterward. So we're just downloading the image. As I said, so we use a tool that allows to set the MUX, the muxing, so it's going to the test system, the dispatcher. We flash using DD. UDD, output will be dev by something, etc. And then we put the SD wire back into the visible by the DUT state. And then we just boot the board. And you see in green a classical U-boot starting with ETNK to start auto boot. So we just interrupt it as usual. And then after that, we send command one by one. So in black, you see the command that we're sending. So we're testing echo, which is quite simple. Testing versioning, testing help, syntax environment variable, printing environment variable to see if it has been working or not, and etc. etc. So you can use everything. And funny thing for you guys, it crashes U-boot somewhere in the middle. Yeah. I think it's here, resetting CPUs. And as I haven't put this string as a failure, Lava does not know about it. That's why it's a bit difficult to make that work correctly, because you have to have all the messages that might happen written in the script. So this hasn't been detected by Lava, but you just need to put that string as a failure, and it will be detected. So just to show you that.
And is the command that's failing, is that a memory write?
I think so, yes.
Yeah.
Yeah.
Okay, cool. It's a bug.
So we can just see the one I just sent has finished. I think it has finished. Oh, it's still running. It's a bit long. Lab, the PDU has some problems. Anyway, just go back to the slides. It's yeah, okay. You see, it's finished. So Going back to it. So it had just finishing booting, and then we run the test. And I think it will crash again for the same reason. Yeah, it's also crashing. Interesting. We found the bug.
So your testing is already proved valuable because you found a bug already,
Exactly, yes.
right?
For me, it's good.
Yeah.
So yeah, we see that this SD MUX way to provision the device is a strong way. But testing and automating the test of a device is really dependent on your hardware. So there are some hardware that also support booting on different media source via their primary bootloader. For example, from internal source like eMMC, NOR Flash, NAND Flash, or from external source like USB mass storage and so on. So one trick can be also to use this different boot capability to develop a strong bootloader provision way. So here is a simple example. You flash your non-working bootloader to the first media. So this is a bootloader you will never reflash again. This is a stable one, which will just allow you to flash the second media. So you boot from the first media, and in the first time you boot from the first media, and you flash the second media via the non-working bootloader. And on the second media, you will flash the bootloader you want to test. And via some automated relay, if you need, depending on your hardware, you will be able to switch on which media you want to boot. So first time you flash the bootloader to test, and then you stop the board and you reboot on the media that you need to test. And with this way, even if the second bootloader and the bootloader you want to test is corrupted or non-functional, you always will have a way to reflash it and to test new bootloaders. So I think that's all for us. We'll present some of the new features that are present in Lava, which can help you to test bootloader. We'll present some tricks with SD wire or media that can allow you to easily test your bootloader. And now, if you have any question, feel free.
So how do you collect the results from Lava? So how do you create test cases?
Okay, so yeah, in the interactive testing, so you have the success and failures messages. So every time Lava is matching, it will create the results on the fly.
For every matching?
Yes, exactly. And you give a name. Every time you send a command, you give a name that will be the name of the result.
Oh, okay.
Yeah, thank you. And I have 3 questions I need to know. So the first thing is if do you have any plan to have the trusted firmware testing? Because it's also a kind of bootloaders, but it doesn't have any interactive shell for the testing. And the second is for Raspberry Pi 3 board, there seems to me there's some bugs in the serial console that if you do some bulk transmissions, then some bytes is missing. So did you have any logic to solve that problem? The third problem is, as your slides show, that there's some boards that might don't have a unique serial number for DFU. Do you have any hardware to solve that problem? Because when the board is made, then you cannot fix the board. So you have to have some thing to work around that.
Okay, so I will answer backward because I remember backward.
Trusted firmware.
Yeah, okay, trusted firmware, so I will understand the right order. It all depends on how you flash the trusted firmware. If it's somewhere we can flash automatically, then it's always the same in Lava. If you can do it automatically with a tool which is working on Linux and reliable, then it might be possible. If not, I think it's not.
Yeah, the point is, what he said is that there is no interactive shell, so that can be a problem. And there is maybe no output on the console as well. Not sure, but that
Yeah, because trusted firmware also can be run on Raspberry Pi 3. So
yeah.
yeah.
So there is no easy solution here, I think.
And how do you know if it's working well or not? Is there something pre-tinned, or how can you test that it's working or not? That is a trusted firmware.
Currently, I also don't have any idea. So, yeah, but
Thank you.
yes.
I guess at least there are traces in those bootloaders. So you can start with output traces. You don't have correctness. I'm pretty sure all bootloaders have at least output traces. So could they be used? You don't have interaction, but at least to run a dedicated boot, get the
that's what
trace and just check as it's what you expect, or you have at least a tag you expect from the trace.
Okay, so right now I'm not sure it will work directly in Lava for a question of different actions, but we do have the possibility, and we use it for Zephyr, for just looking at the outputs and matching some strings, and it will give us the answer if it's working or not. So that's something that might be possible, but it all depends on how the boot and the test are linked together.
If there's no indication in the serial output that things are working or not, then there's nothing you can do. I mean,
Yeah.
otherwise,
Yeah.
even manually, how do you test that? You know?
Yeah,
Sure.
maybe we can imagine talking directly from Lava to a hardware debugger or JTAG and try to test from this, but yeah, that makes the thing.
So that's possible, some work.
Mhm. The second question was?
I don't remember the second question.
There was a second question.
The second question was the serial port, right? So if you have, is this on?
Oh, yeah.
Okay. If you have problems with the serial port latencies on the Raspberry Pi, plug out your USB keyboard. So the reason I usually have seen so U-boot on any platform really is inherently unpreemptive. So everything runs sequentially, which means if you get a receiving a new character and you have multiple input devices, for example, which happens on the command line, for example, and one is serial and another one is USB, you're going through this insanely slow designware USB stack, which then means you overrun your buffer for the FIFO of your UART. And we've seen that plenty of times. So unplug your USB keyboard, it's going to be fine.
Thanks. And the last answer just before Maria, if you don't have any serial number, I don't know of any hardware that can fix it. Maybe
yeah,
some people in the lab might know some.
Yeah, if you don't have any unique serial number, you add more dispatchers and one device per dispatcher. It's not a pretty solution, but it works.
That's another. I don't think it's implemented in Lava right now. But the way we do it manually in the SUSE labs is by just using USB by path identifiers. So you can find out whether what port a device is plugged into, and you just use that port.
Yeah, but that's depends on in which order the USB hub are enumerated.
No, it's physical. It's by port. You can actually find out the genuine USB topology from Linux.
Mm-hmm.
And if it's something serial, for example, you really do have a def serial by path, and that will give you a unique identifier and a persistent identifier for that path.
Mm-hmm.
Yeah. So with some devices, they like the high key when you put it into recovery mode, so you can reflash the bootloader. It identifies itself in a very odd way in the dev serial path, and if you tell me that by path is always the same, and that's persistent across boots, if I reboot the whole operating system, okay.
That's what the point is. I mean, obviously the high key could implement another USB hub behind that port, and then in recovery mode it is something different. But it also, again, is always going to be the same.
Okay.
So it won't change. Maybe you have two different bypaths depending on what the hardware does, but it will always be the same.
Okay.
I do have that's the case for serial converters. The serial number is always 0. So I have to have a fixed path. It's painful to use because if you change anything, it's just not working anymore, but it's working. If you don't just glue your port and it's okay. Other questions?
Okay. Does your system support to download a GitHub project that compile and build the third-party recovery tool?
Okay, so Lava does not compile anything. Lava will deploy binaries that you provide, and if you need an external tool to flash your system, then you have to have that already available inside on your dispatcher before you do anything. Lava will not download something right now and flash with it. Yes. Thanks, everyone.
Thanks.